Check. Hello. Uh, Hope you can hear us. Thank you, everyone who joined with us tonight. Nuan, you can hear me, right? Can someone acknowledge Nuan? Yeah. Um, yeah. So thank you so much for everyone. Check. Yeah. So thank you very much, everyone who joined with us today, tonight. So to begin the presentation, the DLP lecture, let me just formally welcome the distinguished speaker. Uh, so you have joined with us tonight for a specific talk. It's not just a simple seminar or a webinar. It's an IEEE Industrial Electronic Society's distinguished lecture under the distinguished lecture program. We are holding it in collaboration. The main organizer is Industrial Electronic Society Sri Lanka chapter with the IEEE Sri Lanka section, as well as Institute of Engineers Sri Lanka. Today we are holding it physically at IESL Mavsiro studio. So we are coming live to you today from IESL Mavsiro studio. No, they can. Yeah, this is the camera there. It automatically captures you actually. Yeah. Um, right. So our distinguished speaker or distinguished lecturer today is Professor Udaya K. Madawala. He's working as a faculty a professor at Department of Electrical Computer and Software Engineering at the University of Auckland, New Zealand. Even though he's working full time in New Zealand, he's also originally from Sri Lanka. So he did his bachelor's in electrical engineering from University of Moratuwa, Sri Lanka, sometime back. And then he did his PhD, MSc followed by PhD in power electronics from University of Auckland, New Zealand. And thereafter he joined the faculty itself and then continuing as a professor by now. So he's a fellow of IEEE and a registered distinguished lecturer of IEEE Industrial Electronics Society. So he's delivering such speakers all around the globe, and we are really lucky to have him with us today in Sri Lanka section. So he has a strong record of contribution to both academia and industry. He has held various roles in IEEE power electronics as well as industrial electronic societies as well, in addition to his professional career. So he has worked as editorial, advisory, and technical committees member as a technical committee member as well. Also, mainly he served as the general chair of second IEEE Southern Power Electronics Conference back in 2016 and chaired its steering committee. In 2024, he received IEEE PELS, that is Power Electronics Society's Milan M. Janovic Award. So many congratulations to you, Professor. That is from the University of Auckland Research Excellence Medal. So as an long-running academician, He has published over 300 papers and holds a lot of patents, specifically in the wireless power transfer and power converters transfer domain. So today he's talking about very controversial and very hot topic of EV charging. So it's very simple. He keeps it very simple: EV charging challenges and the solutions. Like he'll discuss about the challenges and the solutions, because nowadays everywhere in the world the EV electric vehicles are booming up. Even in Sri Lanka, Professor, we have seen very recently there is a huge enthusiasm towards that one. The main, I mean, even though it's a little bit harder for the markets like Tesla to be established here, still they're there. But the very popular Chinese market, BYD, has opened up a specific launch here, and then we can see. I think you have moved around Colombo. You have seen there are a lot of vehicles going on, but still the charging infrastructure is a problem. So probably you're going to talk about that one, and not like I'm pretty sure that, Professor, you're not just like delivering a speech and going away. So you might be able to join us with Sri Lankan authorities to in the future, how as an advisor probably, how we can continue to develop the EV charge infrastructure. And so we'll see, with the collaboration with the governments, academic institutions, as well as the industry, how we can move this forward. So this will be kind of an awareness session, kind of a deep dive, as well as an awareness session for that one. So thank you everyone for joining with us tonight. So this will be a fruitful lecture. So without further ado, I'll hand over the mic to Professor to carry out the great lecture. Thank you.
Okay, can everyone hear me? And first of all, I would like to thank Kavinda from IEEE for organizing this seminar. Without that, I wouldn't be able to be present here to give this talk. And also like to thank ESL and co-hosting this event. I don't know how many of you have joined IEEE Industrial Electronic Society. And if you haven't done so, I would encourage you to do that. But there are a lot of benefits and etiquette to progress your career. So as you can see, I'm going to talk tonight about electric vehicles, charging and challenges. I'm not going to go into too much technical details. I'm just going to give a summary of some of the challenges and what we can do. Then I'll delve into wireless EV charging, and that's my forte, in fact. And then even for that, I will go from here. So let's have a look at, so because the electric vehicles, all right? Can everyone hear me? It's okay? Well, so the EVs, and they're the, it's a buzzword. So why, and as you can understand, that EVs can be regarded as a means of transport, mainly because they enable efficient and clean transport and that reduce pollution. And it's ideal for sustainable living, right? So ideal for sustainable living, and also, and that the battery can be used for V to X. That means V to anything. Applications, and later on in my talk, and I'll talk about that what is meant by V to X and how we can do that. So, but there's a lag time like there, right? Okay. So you had to bear with that and with some technical problems. And but active promotions and incentives at global as well as the government level. That had led to very high EV uptake, of course, with some challenges. So we are going to look at some of these challenges. And before we do that, let's have a look at the global EV stock. How many EVs are there? The stock. If you look at that, there you can see that from 2010 to 2023, and you can see the exponential growth. And if you take along 2022 and 2023, there you can see a 15 million jump in EV stock. Huge jump. Now, if you go to the global EV stock, why the country, of course, China is leading, as you can see there, and here you can see how it is progressing, 3.8 million to 23 million. So from 2022 to 2023 alone, and that's about close to about 10 million jump. Now, if you go to the second one, this is going to be, of course, US. And there you can see that 3.4 million to 4.8, just about 1 million. And if you look at the cumulative, and that is about 27 million to 41 million, and that's about 14 million within 1 year. So this is just the EV stock. And if you look at the registration by country, so not the stock, by registration by the country, then again China leads. And there you can see 6.5 million to 9 million. And that's about 2.5 million within 1 year. So it is growing from 1.2 million in 2019 and to 2023, 9 million there. And then of course, next one is USA. And there you can see that about 1 million to 1.4 within 1 year, 2022 to 2023. So again, if you look at the total and 10 million to 14 million, 4 million jump of EV registration within 1 year, that is last year. So if you look at the type of the car or the manufacturer, of course, the BYD, which is Kavin was talking about. And there you can see the BY is the leading market player. And in 2022, 1.8 million, and it has jumped to 3 million in 2022. Huge increase. And of course, second is Tesla, way behind, 1.3 and 1.8 million. So what does that mean? So this is the past. So let's have a look at some of the projections that you can see how this exponential growth is going to continue. There you can see there are 3 different scenarios and steps APS and NZD, that's the net zero emissions. And that is from 2023 to 2035. There you can see again an exponential growth in the worst case scenario, and that's with the net zero emissions. There you can see jump from 30 million in 2023 to 800 million in 2035. So what does this mean? So this is what is being projected based on what's happening in the past and the present conditions as well. So obviously there are going to be some problems. So just to again, the global EV sales, they're expecting it to grow 15 million to 100 million. That's a huge jump by 2035. So what are the challenges? And as you can see there, many challenges as this trend is expected to continue. So I'm going to go look at some of the challenges, not everyone, because I can't do that, but give a summary of them, some of the technical solutions, what we can do. Then I talk about EV charging. So here's the EV charging, and there you can see on the left-hand side, somewhere it's coming from the grid. And then on the right-hand side, and you have the electric vehicle. EV in between is the interface, which we call the electric vehicle supply equipment, EVSE. So with respect to each, there are some challenges. And if you take the grid, and you will find that increased supply and demand, we had somehow or other meet this. And also the grid capability, can the grid supply this? And there can be asset overloading, power quality, and as well as unbalance and instability. And if you take the electric vehicle side, and there are some issues that is with the EV market, the battery, charging time, and also the range that, how far they can go by charge, and also the concerns as a user. And in relation to electric vehicle supply equipment, and that's the one that you connect the electric vehicle, it shows over the grid there. Of course, we have to think about the standards, technology, and that's the way we are going to start it, charge it, and the charging rate, infrastructure, as well as the accessibility. So let's have a look at some of these challenges. First one is means of charging. So if you look at the means of charging, and there's the energy source, electric vehicle supply equipment, electric vehicle, there you can see it can be wired or it can be wireless. So either one of these ones. So the wireless is going to be the future, and the wired is already there, relatively simple, less infrastructure change. Standards is the EJ1772. This is at present very easy. We can just connect the cable, but nevertheless, there are some difficulties by doing, especially the convenience. So what the future is going to be wireless. What we do is we charge the vehicle comes and parks. I'll talk about that, and we can charge. Why is it good? Robust, safe, convenient, ice, water, doesn't matter. You come and park and you can charge the electric vehicle. But with respect to wired charging, relatively significant infrastructure change. The standard's already been established, just for J295, but this cannot be deployed everywhere. You can imagine that in the poor countries, it's very difficult to do that at the moment because deployment may be very likely to be in the urban environment there, and that is developing rapidly. So here's the wired charging standards. There you can see that, and that can be in the slow chargers, onboard chargers, and they can be residential, either commercial there. You can see the power rating, and of course the DC charging that is off-board, and that's called the fast charging, and that can go up to 50 to 1,000 volts to 400 amps there. So these are the very quick charging that you can charge your vehicle within a very short period of time, which I will show a bit later. And then, of course, this is the American standard, SAE, and this is the IEC, the European standard, mode 1, mode 2, and also the rapid charging, very similar on board and off board, and there you can see. So I'm going back, sorry, there's a delay here. Charging rate, how fast we can charge. Of course, that depends on the standard, as well as the technology that we use to charge the vehicle, power level, the supply, whether the supply is able to power, and also the electric vehicle itself. Now, charging rate actually dictates the time required for charging. It can be slow or it can be fast. So now the slow charging is superseded by the latest DC fast chargers. And what they say is that offering less than 20 minutes, even less than 10 minutes charging, you can charge. So just to give an example, here's a shadow, and there you can see the 120 kilowatt unit fast charger. So these are off-board chargers. You can quickly charge the electric vehicle. And then, of course, the Delta Electronics 100 kilowatt charger. And there's another charger. You can see that by charge point, and they can do that. You can see that from there, it's 125 kilowatts. Here, charge here. And then the much faster rate that you can charge, 500 kilowatt maximum from charge. So this is the technology. It's already been developed. Now the question is, yes, we can charge quickly. Can the battery take it? So if the battery technology is growing at the same rate as the charging, that should be okay. So let's have a look at what's going to happen. Shift delay is very difficult for me to continue because it's a big delay. Let's continue that. Okay. Driving range, that is distance to charge. So this is increasing at a moderate level, not the level at the rate that the EV uptake or any other technology. And if you look at that, and here you can see that small cars to average car, at a large, medium, average car, there you can see the number of kilometers that you can from 2015 to 2023. It's a moderate increase there. So per charge, how far you can go, it's not increasing rapidly, but nevertheless, this is what the manufacturer says, and that this is depending on the battery capacity of the electric vehicle, of course, large battery capacity. And also the lower range and causes range anxiety. So what can you do? So the new models of the cars, as you can see, and they are going to, they are offering nearly 250 to 370 miles on a single charge. So that is promising. So by 2030, battery EVs are assumed to reach an average driving range. Yes, miles, yeah. So it's about 400, 450 or something. Uh, so you can see every driving range is 350 to 400 kilometers. The battery has, that all depends on the battery size. So 70 to 80 kilowatt hour battery, and this is the range what they expect. It could be 250, 370 kilometers, I can't remember. So solutions. Hmm. Yeah, that's the latest one. Yeah, that's what it was. Yeah. So solutions. One is of course the battery, that you can charge quickly, have the light, can travel further. So easy access to charging stations, more charging stations. Because just because you have more charging stations, if they cannot be accessed easily, it's no use. It's a very important thing. That's a coming under planning. I wouldn't go into too much detail. And then the battery swapping is another technique. And some are actually proposing battery swapping is much better. And they said that they can do that. So you go to a station there, you swap the battery, charge battery. So the other one is the dynamic or in-motion charging. And that is one I'm going to talk a little bit later. At the end, wirelessly as the cars move at 100 kilometers hour, we can charge the battery. So that's going to be the future technology, especially for heavy duty EVs. So these are called electrified loading systems. So then we look at the battery. Of course, there are some concerns with respect to size, weight, cost, life. And not only that, at the end of life, disposal, what we do. There are millions and millions of cars. So lithium-ion batteries they are the high energy density, 100 to 260 watt hour per kilogram, but they are still significantly heavy, bulky, and expensive. And for an example, if you take the Nissan Leafs, it's for 24 kilowatt hour battery, it weighs 200 kilograms, whereas the Tesla, 40 kilograms, almost half a ton. So the cost, the cost down from in 2010, it was almost $1,000, 1,250, and the kilowatt hour per kilowatt hour. Now it is coming down to 150, and they are thinking that it's coming close to about 100 in 2022 and 2023. Why that is what the GM said. I don't know it's coming down, but I have some figures here. You can see that. So what the battery cost there, you can see that it's coming down and down, and they expect it to be quite low when it comes to 2030. So not only the cost, the energy density, because if you look at the energy density of the battery is quite good, but the power density for power is less in comparison to supercapacitors. But it is now reaching the supercapacitor level, and that's what the battery manufacturers say. So the new battery technologies are coming up, and as you can see on the left-hand side, it's called solid-state batteries by QuantumScape, and what they say is lighter, high energy density, more range, lower cost, and faster recharge times, but it is far from ready. It's in development. And then on the right-hand side, that you can see the new batteries are coming, and these are called the lithium-ion cell with nickel foil, and they are meant for very good for air mobility services. And also the new battery technology, this is the company that is from China. They are working with BYD, and there you can see that, and their life is going to be 1 million miles, 1.5 million kilometers, and the 15-year warranty to batteries. So this is the latest technology, and you can see the recycling and how many cycles, 1,000 cycles to do. And also new one, BYD again the same, and you can fully charge within 10 minutes. And that's the latest that they're actually working with BYD. And this is another new battery manufacturing battery technology. And these are called the hybrid sodium and energy storage devices. And as you can see that they can charge at 80% in just 9 minutes. So this is going to be the future. So now I talked about the type of batteries and the technologies and etc. So let's have a look at the battery life, and that is very important. And normal battery life with the span is about 3 to 8 years. And that is equivalent to about 100,000 kilometers. So the question is, as of everyone else, when it reaches the end of life, or the retirement, what you're going to do? So the one option is the recycle. In other words, we can get some of the components or recycle, and we can use it again for different applications, especially for energy storage, etc. Or else we have disposed it. So if you look at the recycling capability in the world, there you can see, and the main capability is in China. And you can see in red there, and they have the capability. And that is by 2030, they had the largest the capability for recycling. So this is a very, very important thing. Millions of cars going to be there. And we had the prediction there, then we have to have this capability because otherwise we have disposed it. That's going to be a big issue. So, and the other issue is I told you about that, and you can charge the battery so quickly. But what will actually happen to the battery chemistry? And a lot of people are now working on and how we can make sure, yes, the technology has developed to give so much power, but can the battery take it? What will happen to the battery life? And people are investigating on that. And what would happen actually, I have done some work on that too. And how do we improve the reliability and the life, etc. under these circumstances? And what they normally do is this to address this concern, there are numerous battery health monitoring, we call the BMS systems we propose and implemented. There are so many thousands of sensors there, and they control everything there so you can charge the battery. But, and that is a concern because the technology is there for charging fast, giving power, but the battery, can the battery take it is a question. But the Chinese manufacturers improve the battery technology. Now, as explained before, you can charge the battery within less than 10 minutes. So that is about the electric vehicle battery. Now let's have a look at the impact on the grid. So when I talk about the impact on the grid, and there's two things, demand, many electric vehicles, you need energy. So you have to give that energy for the demand. That's the demand side. And of course, when you have the demand, that has to be supplied by the grid. Where does the energy come from? Energy has to come from somewhere. So this is electrical energy. It has to come from somewhere. So this is due to the high uptake, multiple integration. Just imagine millions of cars connecting at night to the grid. It will happen. It's a huge problem. So they both increase energy and peak power demand. Not only the energy I'm talking about, the peak power. So there's time, especially at night, what time, and everyone is using electricity at the same time to start charging, it's going to be a problem. And then, of course, the increased energy. We need this electrical energy to come from somewhere. We have to generate more. Where does it come from? And the other question is that more and more countries, especially UK and China, for example, and the car manufacturers, Honda are moving to full electric by banning manufacturers' sale of all petrol and diesel vehicles. And this actually further compounds the impact on of electric vehicles on the grid. So it's a big problem. So if you look at here, so this is what they said in 2017. They said the UK's aim was to ban petrol cars or diesel 2040. Now they have moved to 2030. And that is what they want to do. We cancel this one. So if you go to Honda, one of the manufacturers, there you can see they want to go completely get rid of petrol and diesel in 2040. So they want to go for fully electric, also the fuel cells. electric vehicles there. So that is their aim to do. And not only the cars, and even the scooters, they want to be fully electric. So that's what's going to happen. That is by 2040. So you can imagine now, we need energy from somewhere, and this has to be supplied by the grid. How do we do that? Huge challenge. Demand is very slow. And here's electricity demand. You can see that for different scenarios. And there you can see that from this on 2020 to 2030, jump of 20 terawatt hour to 550. It's a huge jump. So you need this much of energy to meet this demand. If you look at the peak load, there you can see, especially in China, even in China, 12% off, nearly 12% of power. And that is due to the demand for electric vehicles. So how do we do this one? It is all good that governments giving incentives and promoting, and when you global level, they use electric vehicles very good, and all the greenies and saying that, okay, we have to cut down all these emissions. Yes, very good. But nevertheless, energy has to come somewhere. This has to be met. Even if we can meet this energy demand, do we have the infrastructure to do that? And that is a big question, the existing infrastructure. So you have to augment it or completely renew it. What can we do? So that is a big question. So the one way to get around that problem is you can do some sort of an intelligent way of with incentives to charge. It's called the V1G into one direction. Okay, so the vehicle from to the grid there, not the other way around. Actually, it's a vehicle. Okay, so it can be somewhat can be reduced for 4% by optimizing smart charge. But this is not the solution. And what we did was, I'm just going to show you a slide. Asset overload, the other problem, asset overload. So if you look at this one here, and here's a scenario that 4 different scenarios, different level of penetration of electric vehicles to the grid there. So the higher the penetration, more impact on the grid. Now here it's the asset overload. Here we have the feeder line. You can see that almost double feeder load in there. The worst case scenario for electric vehicles. Right? And then if you go to another one, so when you have the feeder loading much higher, the asset is going to increase too. So system level, there you can see how much power is lost or energy is lost. So we did something, because I did some work for Indonesian government for the power company. So they want us to find out whether the existing system and the worst case scenario can cope up with this EV output. So we did some analysis and we came up with a solution there. So this is sort of a system level approach and how we can do that. Then we keep looking at the transformer for the loading conditions, and then we can do some smart charging. By doing the smart charging, even if we have much higher penetration, because still we can use the system. So this is what we did, and this is how we charge with some incentives and etc. I'll just show you some results. And there you can see. So we have used 4 different scenarios. 4th one is the worst case scenario. And there you can see this with the transformer, 630 kV distribution transformer there. Oh, I'm sorry, I don't have a pointer even here. Right? There you can see that at night, and the worst case scenario that exceeds the transformer capability. But what can you do? So this is what's going to happen. You can replace the transformer very quickly. But even replace the transformer, you can see, and not during that period. So it's no problem. So what we can do. So we did with the smart charging, what I showed before. There you can see the worst case scenario. It is still well below the capability of the transformer. Use it. So this is another scenario and the same transformer. And we monitor the transformer capability there. There you can see under worst case scenario, the voltage drops. But this is not within these two, the given application by the electric supply. So well below that, but we meet that. So there you can see that we use the same conditions there. So we can actually restore the voltage under the worst case scenario too. So there are ways of doing that, but still it is going to be limited. But with the growth of electric vehicle uptake, we come to what we call. So the problem is the unbalanced conditions. And there you can see phase YC is unbalanced. And I think that is yellow line here. Okay. Okay. Yellow phase, there you can see, and it is much, much higher. So what can you do? And I just give an example. You buy an electric vehicle, your house is going to a particular phase in the vehicle system. How do you ensure that you can't select, I want phase A, phase B, that is, it is not loaded, but you can't do that. So what do you network there and not overload. So how can it is overloaded and you can show that it's going to be increased. So what can you do? There are some manual ways of doing that, but it is very cumbersome. So how can we put it up this electronically? And I'll show you some of the work that we did. Okay. So that is a problem, and also the harmonics and the power quality. Everyone is connecting, but this is tightly regulated, so therefore you get harmonics. But nevertheless, it's a problem. So one of the electronic solutions is what we did, and we did the multi-purpose fast EV charger. There, what we can do is when we have the EV battery, and then we can use the energy storage to put the energy to meet the load and to balance the load. And also, in the other mode, if still the load is unbalanced, we take selective phases, power. So in that way, we can actually control the currents in each phase of the electric supply. Now, I'll show some of the results. There you can see the unbalanced grid currents there. There you can see the grid. The green one is much higher than the red and the blue. So what we can do is with our method, we can actually improve it. There you can see that they are going to be all balanced. We are still delivering the same load, still charging the electric vehicle. You can see it to the vehicle. So we do from each phase certain amount of energy, you could say, and in a manner that all the grid currents are balanced. So that is one way of doing that. And I will show you the V to G mode. Same thing. Now we have the battery, and we can meet the load, and we can put the energy back into the system there. And there you can see all the grid currents are balanced. So there are different ways of doing that. And there's another one we did. And this is the latest technology that we have developed in the university among my students. And there you can see that I can compensate. I can do work compensation. I wouldn't go into too much details about that. And the voltage imbalance, the current imbalance, I can have a battery storage, and I can do everything. And this is actually a hybrid transformer. And we have the existing transformer here on the left-hand side. You can see that. And this whole converter system can be just connected. It's 20% so I can deliver quality three-phase supply. So I'll show you some of the results on this one, I think. Since we built and tested the system, there you can see that how the grid voltage is. As you can see that this is the unbalanced conditions. The grid can be still balanced because injecting voltages into the grid. So the voltage sets, and there you can see the voltage rises. Up here you can see higher than what we need. Normally we use the what you call the online tap changes, but so this is, you can see all the big load voltages are not balanced. Unbalanced voltage, you can see some of the voltages are unbalanced, so we can balance it too. Then of course, charging infrastructure, which I was talking about. Can we deliver this much of energy to electric vehicles? That is, or do we have enough chargers? Let's have a look. There you can see the white dots. I mean, is it the, as you can see that is charges per electric vehicle. How many charges per electric vehicle? So that is on the right hand axis. You can see it's about in 2023, or this is a different scenarios. It's about just over 0.03. So that is the number of fast charges per electric vehicle. So if you go to 2023, 2035, so 2035, it is less than 0.02. So that means that we don't have enough charges. And this is what the prediction is going to be. So we need to do something about it. So that the fast charges, slow charges, it's a home. So I'll give you more another example. I'll look at this one. Charging infrastructure. There you can see the private slow charges 6.5 million. I think this is 2023 as I recall. Publicly accessible 500,000, and publicly accessible fast charge 250,000. But if you can remember, we had millions of cars there. So many millions, but what do we have? So we are far behind. We need to do something about them. Now, this is another scenario. This is called the road to zero scenario, right? Zero emissions. There you can see if you take Germany, 6% the total charges they have. But if you look at the Germany and that was, and today, as of today, last year, the year before this one, and they have less than, I don't know, about 25,000. And if you go to the next one, 300K, and that is in 2025. That's the prediction. And then 2030, 700,000. But this is not the case. This is what they need. But we don't have this control. Not even around the world. So what does that mean? Insufficient that percent. We can't keep up the rate of increase of EV take. We can't do that. And so we need to upgrade the power network or complete very costly. We'll come up with some solutions and we need to do some planning. And what is important is when I say need planning for future, only the EV manufacturers, so the charging suppliers, the government can be private entities. They can't do it alone. They have our network operators there. They had to put strategically. It's convenient with the transformer cable. They had to plan all these charges and what's going to be. So this is going to be big everywhere in the world. So now the next one is I'm coming to our EV is only for commuting. So if you look at here, and this shows that most of this energy storage is coming from electric vehicles. So you can see how much from 2025 to 2050, the blue. And there you can see the amount of energy that can be stored in EVs. That's what is available. So we can use that for some of the applications there. So that is called the V2X and the V2X. I'll show you what we can do. V2X concept. The X means anything. And of course, you know that V2G concept there and off peak time that you can get the energy. V2G. So then now they are doing V2 building to home with loads there. So you can use the electric vehicle, you can go plus or one single electric vehicle. And also, I talked about this long time ago. People laughed at me. This will never happen. This will never happen. V2V. And the vehicle to vehicle. And I'll show you some of it. Technology so we develop. You can do that. So we look at, so this is called the V2X. But in order for V2X to work, and you have to have some capability. Here on the left hand side, the entity, and the right hand side is electric vehicle, it will be battery there. In between is the bidirectional charge. So you need to have a bidirectional. So the energy can go back and forth as required. It's all regulated. So this is Nissan Leaf to Home. And this cannot be 2012 or 2014 and that time, but this cannot be good because still the standards not released and you can allow your 2 days. So this is a Chademo Leaf to Nissan Leaf to Home. And this is a three-phase. And again, the V2G system there. And some of the latest one, V2G or V2 buildings, the latest Nissan can do. But this is already now available. And all the new electric vehicles, now they have bidirectional. They all, when you buy electric vehicle, they all have bidirectional. Doesn't mean that you can put the energy back into the grid, but they have the capability. The reason being that the standard being implemented and be released. So you cannot do the safety reason. You cannot. But you can definitely power your house or emergency, you can use it. Off grid. This is V2V. And there you can you see the cable? There is the cable. There's a video there. The cable there, what's the V2V? So another vehicle can come and charge there too. And in fact, there are some systems that angel of each segment charging and so let's go to wireless EV charging. So this is about wireless EV charging. So this is based on inductive power transfer equilibrium. So what actually happens is here we have a grid, what's the energy source. Then we have a coil, which we call the charging pad. This is very the ground. And then we have an interface. So what that interface do is that it is an AC to AC. The interface I'll show you in a minute. And the car comes and parks on top of the charging coil there. And then what we do is we get the low frequency and then we convert it into very high frequency, standard 85 kilohertz. And what actually happens is we excite that coil, so high frequency magnetic field. And underneath the car, there's another coil mounted there. And through the, and as you can see the magnetic field, and through the magnetic field, power transfer takes place across the air gap. And power is transferred from the charging coil on the ground into the what is known to them. So this is called like, so it's very developed. And so this is what the car manufacturers and all those future cars. So this is called the stationary charging because as you can see, the energy is coming from the grid to the battery. There, actually, the one we started doing with the vibrational charging. And then you can, energy can go back and right. So that is for the V2G and V2V applications. So how does a typical IP2 system work? And there you can see the two coils. And they're separated by so the transmitter, receiver, things. So they're separated by an air gap and they are mutually coupled. Inductance there. And then we have compensation. Compensation means that because of the so when they don't in order to transfer from one side to the other. Is that okay, we indicate the reactive component there. Transfer power very efficient. So then we have a DC to AC converter, and then what normally is the 85 kilohertz for electric vehicles, and it creates it generates a high frequency 85 kilohertz signal voltage there. So the current that is going through the coil is 85 kilohertz, magnetic is 85 kilohertz, it's total. Okay. And then through the magnetic field and through the coupling, you can see the energy is transferred from across the air gap from one coil to the other and at 85 kilohertz. So that is rectified and you get a DC, and that's the load. So on the primary side, then we have a grid there, but it's low frequency. We convert it to DC, and then again going to high frequency. So this is a typical system. So the power flow can be in one direction. And this is actually the ground assembly, GA, and this is called the vehicle assembly. And the power flow can be in one direction, or power flow can be both directions. So we can control the motors to regulate the power direction flow. So this is a typical system. So there are four basic types of compensation networks. And there you can see that then they have different characteristics. This is not important. You can connect the capacitors in series or parallel to minimize the VAR requirements. It's operating at unity power factor. So here's the standard for wireless EV charge. It's all been released, J2954. For the light duties, and they're working on the heavy duties, and they're looking to safety, performance, different types of pads, communication, EMF levels, magnetic, electric, and live object detections, living object detections, and everything is covered by the standard. And EVs are expected to be compatible. If it is a wireless EV charger, it must be able to charge the car with wired chargers too. And the frequency of operation, the power transfer takes place at 85 kilohertz, but the frequency can change between 79 to 90, but you have locking to one frequency, as I understand. Transfer power, efficiency is minimum efficiency when the pads are aligned, 85%, and if it's offset is 80%. And here are the power classes there for wireless charging. So 3.7 kVA to 11 kVA. Normally now they are saying the 20 kVA is another class for that is coming on the heavy duty. But at the moment, this is all being released and the cars being tested, and I'll show you some. So now the question is, I talked about that. We must be thinking, is this possible? Yeah, it is. The Vitricity in the payload receiver. This is some technology that developed at Open University. So this is now working with the Vitricity that we use. And that is the, you can see the pad or the coil underneath the car mounted. I'm sorry, I can't use this on there. Silly, okay? So that is underneath the car. And that is the what is on the ground. So the car comes and parks, and you can charge them. And that is the Hyundai is using it, and I have a video there. It comes and parks the wirelessly charges. And there's another company doing the wireless charging. Oh, a lot of car manufacturers. There are many applications I have. And there's another one for the pad and the misalignment. So the car comes and parks. Of course, in modern car, you can maneuver the pad behind them, but nevertheless, it's difficult to align. If it is not aligned, what that compromises the amount of power that is being transferred and also the accuracy. But there are two ways of mitigating this problem, and I'll show you one. One is the passive, and that comes there. There you can see on the top pad. So the left-hand side is the primary coil, the grid side coil, on the ground side. Right-hand side is the electric vehicle. On the top blue shows that the capacitor is connected in parallel, whereas the bottom side, capacitor connected in series. So what it means is they have different characteristics, but they are complementary when the couple between inductance. So we can have constant power transfer. Still, from there you can see that, sorry, there's a time lag. And you can see the one the x-axis shows that the misaligned changing the distance there. And you can see the one system, the power decreases when the other system power increases. When you combine them together, you get constant power. Show you a video. Over 3 kilowatts. That is called passive. Now we can do active too. And we don't have to do anything. We have this system, it's a typical system. What we do is, and I did this work, and as you can see here, two converters, and we control the two converters, and then four variables there. And with optimum voltage, two voltages, frequency, the phase angle there, I control. I measure everything there. If the coupling end changes or due to, because this is a resonant circuit. If it is due to or coupling changes, the power transfer is affected. I control these two variables. They are the maximum efficiency only by controlling the converter. So I can regulate the power, maximum possible efficiency. It doesn't matter about. I'll show you some of the results. And this is some of the systems that we built. There you can see with normal oil control. And there you can see from here, A, B, C, different coupling. That means the coupling has changed. But still, we can bounce from 200. This is for the 1 kilowatt system there. Maximum efficiency in comparison to oil-based control. See, the blue curve is oil-based maximum. We can regulate power. So there's another one here. And there you can see the coupling changes from different couplings that you can see that still my blue curve is the maximum power. So then the wireless V2X, and that is power is going one way. So can I do both direction? So this is what we do again, and I started this work about 15 years ago. And there you can see what we do is we control the power flow by controlling the flow. And I can actually change the direction, and I can regulate the amount of power that related to each other. So this is what we did, and I won't go into too much technical details, and depending on the phase angle of two converters, relative phase angle, I can control the direction of the power flow, the amount, and I'll show you. This is what we first built about 2010. That's the first thing to build. And we have come a long way since then now. We can transfer power both ways, much high power level. And there you can see that the power thing. So that is the gap is about 400 millimeters. So that was our initial work. And since then we have come along. So you must be thinking whether this is good or not. And this is the license to electricity for the Honda. And they are doing this work, and for the Honda is doing it cheap price. I'll skip through this one here. This is how the business work during the time. What's the time now? Okay. Okay. One more thing what we did was, so if you look at here, now the electric vehicle, it comes and parks. It has to be connected to the grid anyway. You come home and park the car into the grid and, sorry, connect to the grid. And there, this is your, I'm sorry that I don't have a pointer, so I can't do much here. So you can see on the right-hand side your nonlinear household load. So it has the active power, reactive power, harmonic power. This has to be supplied. Normally it is drawn from the grid. But when you connect the interface and then the electric vehicle, actually we can use the interface in an intelligent manner that to supply everything what is required by the house. And so what is drawn from the grid is only the active power, will be power. So we implemented this system there in a very efficient way. It's all wirelessly. And I'll show you what active power is. And this can be operated in 5 different modes. And as you can see that only the grid gives the active power, household power, and the electric, there's no electric vehicle, but still the interface is there. It will give all the harmonic and the reactive power of the house. So nothing is drawn from the grid. And the second mode is grid to vehicle to home. In other words, grid is actually charging the electric vehicle, also giving the active power to the household, but all the reactive and the harmonic power is given by the interface to the grid, so the vehicle. And the next mode is now the vehicle has more power, more energy. It's not going to be used at home. It can power the house completely. Excess energy can put into the grid. And there, of course, here's the grid and is giving the what is required for the load. And now again, the because what is in the vehicle battery is not enough to supply the household. So only the active power is drawn, whatever the what is needed from the grid, unity power factor. And this one is no grid, everything is powered by the electric vehicle. So we tested this, so I'll show you some results. There you can see the first part. You can see that is the nonlinear load from the house. And this is a small system that we built. And as you can see that in this case there, actually the load is about 430 watts and the electric vehicle is giving supplementing the power that is required. So put in, that is why it's called the vehicle to grid to home mode there. So both the vehicle and the grid is supplying the power, all the reactive harmonic given by the vehicle interface there, nothing there. So reactive power from the grid is 0 and unity power factor. And this is the islanded mode. And there you can see that there's no grid. Everything is taken care of by the electric. And this is another one without the vehicle. And still all the active power is taken care of by the grid, whereas the harmonics and the reactive power taken care of the interface. And the next one is the grid is charging the vehicle and also supplying power to the house. And reactive and harmonic power is made by the interface. Okay, so something that I want to talk is very important. And this is what he was talking about. This is called the dynamic charging. And that's called the charging while in motion. I think this is wrong what I read. Okay, moving with pulse power. Okay. There a mistake there. So this is what happened in future. Now this has been tested. I'll show you. So there are dedicated lanes and there are coils buried the ground, dedicated lanes there. As the car moves from one pad to one coil to the other, synchronized, and the pulses of energy being generated pass wirelessly. So that is going to be the future. Right? So this is so you had to generate pulses of energy, but 20 kilowatts. Cars can move 100 kilometers per hour. It's still charged wirelessly. And this is what is happening. As you can see that how the ground coils are energized sequentially one at a time. High, so the vehicle is moving. As the vehicle comes on top of the car, we can detect it. and then we can see the pulse of energy. When we as the vehicle moves, we can charge it. So this is going to be the future, and this is especially for the electric heavy duty trucks. They are going to do it so that they can reduce the battery size and the weight. So that is quite efficient to do that. So this is being tested. This was done in 2016. And our group, and I'm not actually directly involved in this one, nevertheless, our group, they were involved with Qualcomm and they tested it in France. And you can see the 50 millisecond pulses of 20 kilowatts generated at 85 kilohertz to charge as the vehicle is moving. I'll show you some of the programs, and this is some other countries have already implemented. This is in China. And as you can see, the car is moving. And this is the buses, and when they are moving, you can charge them. So this is already been tested. So with this, I will actually I need to go speakers and that one there. Okay, so I will with this I will conclude my talk. I'm very happy to answer any questions. I apologize because it's very difficult for me to it affected my flow because very difficult without having a point and everything to do that, and also delay from my computer to the screen. Okay, thank you.
So I think now the floor is open to the audience. So you can unmute yourself from the online audience and ask any questions that you have from the professor. I think it was a very interesting topic. Everyone is very enthusiastic about this particular topic nowadays. I think even though there are so many deep technical details that Professor and his team is doing, you try to bring to match to any audience, like anybody who can understand it interestingly. So anybody, if you have any questions, you can unmute yourself and ask, please. So there are some questions coming from the messages books as well. We'll see. Yeah.
Okay. The question is how do you see bidirectional charging impacting grid stability in the next decade? Are there risk mitigating strategies in place? Well, I think the bidirectional charging is quite important in the sense that it's not the risk. Bidirectional charging, the V2G is already, it has been a concept for a long time. What I'm doing is in doing that in wirelessly, do it. So in fact, having V2G concept, whether it is wired or wireless, it actually improves the stability of the grid because you can put the energy to stabilize the grid. So in that perspective, I think it is very important, it's very beneficial. And not only that, the V2G concept or the vibrational cable is very important. And some of the applications are people talking. Just think of the tsunami, cyclones, flooding. There's no supply, an emergency supply, and you can use electric vehicle. So it's very important. Okay. I hope that I answered that question to you. Good question. Thank you.
It's like even if you go on a kind of outstation picnic, so you have to bring separate batteries, but without instead of that you can use the so, so I mean
Yeah, but there are some protocol, right? Right. If it is okay, yeah, we cannot have energy back. I didn't talk about the protocol. And when you're charging and discharging, there are protocol. Maybe you can profile.
right. Yeah, of course, like when you're dealing with the technology, we also always have to like adhere to the manufacturer's advices. Otherwise, it's so dangerous. Like all these dealing with the batteries not something. So I have like very generic questions, not very specific. This is kind of generic regarding the EVs. So people are talking about the EVs, and then like people are pushing because now you cannot. They're saying that okay, you can. This is coupled with the renewable energy and so on. But still now, if you're charging it from the grid and so on, still you are using the main power sources, right? So, what is the how do you convince somebody like saying, okay, instead of a fuel vehicle or probably even a hybrid vehicle, uh, how can we convince, okay, you are using less non-renewable energy uh, using EVs. And then, I mean, it's not just about the steady state using condition. It's all about, like they're preparing the infrastructure, batteries, and so on, because they are also.
Okay. So that is a good question, Kavinda. Okay, the question is about that. Okay, energy has to come from somewhere. Okay, so EVs are good; they reduce pollution, and that's good for sustainable living, and it's very important. And also, yes, uh, it reduces the amount of fossil fuel use. Because why I said that word is that energy has to come from somewhere. So the plan is one other thing is that, and sometimes even if you do use fossil fuel, because you had to generate electricity, let's say that gas turbines, example, it can be at a distant place, but still that is can be generated, but we are not completely directly using in an internal combustion engine, so electric vehicle. So that what is the pollution that is coming from that one that can be taken away from the heavily densely populated area. That is one thing. Terms of population, for example, pollution, even the coal, right? Now, that is one aspect because that energy demand that is required from electric vehicle needs to be met. So what they are saying is that more and more renewables going to be used. So instead of so therefore, and also the nuclear power. So that is what's going to happen. But whatever the case, whether it is happening or not, energy, you need to generate more energy there. So where it is coming from a different story, but the incentive, and the encouragement is to use renewables, mainly solar, maybe the wind as well, and then the nuclear. That's nuclear is going to be. Some people argue that just to be it's like renewable, that is clean. That is what they say something. Renewable is going to just come from somewhere. And, we had a session with probably you know him from IES with Professor Dimitri Minikov from Estonia. So he was mainly talking about the building decarbonization, but that is back again connected with EVs. So he, he has been suggesting something like, okay, building is he's more suggesting the off-grid solutions where you keep off-grid solar power system or something like that. And then with that itself, you consume some of the electric energy where your home needs. I mean, not just a home, it could be any sort of a building. And then the rest of the energy you can use to charge your vehicles. Probably if it is an institutional building, in the daytime, people might come and then you can charge your vehicles. But if it is your vehicle is at your house at the time where the solar power is not generated. That is exactly what I talked about the V2X concept, V2 building, right? That is what it is, right? But nevertheless, that amount of energy I showed you has to come from somewhere. So the solar may not be able to generate that much of energy. It has to come somewhere. It has to be generated. So what are the key bottlenecks in scaling EV charging infrastructure in countries with less developed like Sri Lanka? So I think it is not only in Sri Lanka, the many countries, because I know I was reading that the global EV outlook. Actually, quite interestingly, I saw that New Zealand has the most number of electric uh, charges, EV charges per person, per vehicle in the world. Because we are a small country, the number of the charges that we have. Now the question is, what are the bottlenecks or the problem associated with that? It is because basically the distribution network will not be able to cope up with having more and more electric vehicles being connected. That is one thing, because either they have the lines to be replaced, transformers needs to be replaced, or some other mechanisms. At the moment, they may be okay with putting some penalties or some, higher charging rates and discourage people connecting to the grid at the peak time they can do. But then again, that's not going to solve the problem. And the smart charging, optimized charging, you can do it to a certain extent, but nevertheless, at the end of the day, in another 10 years' time, you saw the number of electric vehicles going to be to the grid. The grid needs to accommodate and this demand. Without that, we can't do it. So that's what I think. And Sri Lanka will have the same problem. Already you have problems here. I don't know if maybe aging network. I don't know how it's operating here. So they need to upgrade it. And also there's another question. Is there any standard V2V? I actually don't know V2V change standard. But as far as I understand, if I think about that, whether the vehicle is used to discharge, get energy, retrieve energy. The vehicle doesn't know whether it is a building or a grid or another vehicle. So it doesn't matter. It's been in the protocol, and they allow the battery to be discharged. So that's what I think what's happening with the vehicle models that I showed. So it's the same technology. It's a matter of, enabling or authorizing the discharge, taking the energy away. So how to get free certificate? What does that mean? How to get free e-certificate? You understand? Sorry, I couldn't understand. There's a question for how to get free e-certificate. Can you elaborate on that, please? I couldn't understand. Yeah, don't feel bad about that asking questions. I know a lot of people, they don't want to ask questions. I'm okay that if I don't know, I don't know. That's fine. Yeah, sure. What's the question from the
Yes, thank you, sir. It is a very informative session. I think that I have a idea about I'm going to buy a new car, electric vehicles in this year, end of this year. So I have a few question. That's a general question. The out of Colombo area, we had to face more difficulties to charging system. I think that in Sri Lanka, I think few charging point out of Colombo area, like Anuradhapura or other Jaffna area, something like that. So what type of solutions, what kind of, we can take some strategies for that in this stage in Sri Lanka? Is your idea about the charging then by using like that
charging stations in Sri Lanka? So when you go out of Colombo, what you can do? And actually, I think that is quite difficult. I don't know. In my opinion, only way what you can do is you have to find a place. But given the range, you may have to, I think there on the internet that you can find where the charging places are. And you may have to work out that, okay, this is where I'm going to go. But normally car indicates how far you can go. Okay. And then you have to stop over, charge. I don't know that there are fast chargers here. So that might take a long time to charge. but there's no other way to do that. Then you have to put overnight charge there somewhere. You have to stay overnight and you charge. So that's the only option as far as I know. I offered. I don't know. I offered without anything really advice. If they want my opinion, I'm pretty happy to come and serve Sri Lanka. But I listened to them and saying that, hey, my expertise and very happy to. I have some other things I did some with some other countries. As I told you, I did with some Indonesia as well. What to do, and also I didn't go into too much details about how to do the planning, carbon planning, charger planning, etc. But that's a different topic for this case. I mean, it's a common problem. So didn't go into too much technical details. Very happy to help. Yeah, very happy to help. If see who wants it. Yeah, any other questions? Or you can email me too. Anyone else? Yeah, please. So probably some of the joined here might be already undergrad students, or they might be the early career, like young professionals. So if there is any opportunities that you can they can join with your research teams or your organizations, like if there is anything, how they can contact you and so on. Yeah, just email me. I have already given scholarship to students from Sri Lanka, and they were with me and they settled in my river and also Australia. So contact, I'm helping a lot of students during the leave. Yes, we contact them, just to help to help. Because I came from here, studied life, just to New Zealand, life is a thank you so much. And moreover that we will see as we discussed, like I mean, providing more opportunities for the students to come there and do researches and join these activities, as well as if we can like establish some partnership within Sri Lanka and New Zealand, something that people can do within Sri Lanka and do something back to Sri Lanka to develop these infrastructures and so on. We will see. You can come with the government. Yeah. Right. Yeah. Yeah. Of course. Yeah. That will be great. I do apologize because I don't. I like this is very difficult for me. Yeah, and I send the audience engage and the delay. I couldn't. Yeah, very difficult. Oh, right. No, that's fine. Right. But yeah, but at least a lot of people engage with the Zoom meeting. I joined and checked, so that is at least good. So hope it went really well. We have the recording as well, so we will distribute it for the people who couldn't join with us tonight. So with that, we are going to conclude. Thank you very much for everyone joining. So hope to see you once again with a similar lecture in the future. Thank you so much. Thank you.